Yes, we know that breeding dairy cows for improved feed efficiency, it requires data on dry matter intake. But on-farm measurements are expensive and very laborious. Marker methods, they have mainly been used in grazing conditions, but to measure feed intake using internal and external markers in barn conditions, it is very labor intensive. There has been some successes of using three-dimensional cameras predicting feed intake, but both accuracy and precision of these methods can be questioned. So far, breeding for improved efficiency has mainly been based on dilution milk production to create dilution to create a volume of milk. So proportion of maintenance requirement has decreased, but future potential of this is rather limited because at the moment we have high production levels in dairy cows, and especially if body weight continues increase as it has increased with increased production level. So this is picture of partition of feed energy in dairy cows. I think this is familiar for all of you. What we need to rank the cows for feed efficiency, of course we need to intake, undigested residue of fecal energy, methane and urinary losses, we get metabolizable energy, and then heat losses and net energy in terms of body energy tissue gain, or if we are in milk production, then it is net energy in milk. So we need to know at least most important components of this to be able to rank the cows according to feed efficiency. Next, please. In respiration saver studies, carbon dioxide production was actually better predictor of a feed intake than energy-corrected milk and metabolic body weight or body weight that we commonly use to predict feed intake. And it also improves intake prediction when we added that as a third variable to this traditional model. Dry matter intake is predicted from energy-corrected milk yield, metabolic body weight, or directly from body weight. And these deviations or this improvement, it reflects differences in feed efficiency. We collected a large data set from respiration chamber studies of almost 900 observations from Hillsborough, Northern Ireland, Folum, Denmark, and Luke, Jokioinen. We divided the cows into different groups of in feed efficiency, or made statistical analysis how this residual feed intake or residual energy corrected milk yield was related to different energy losses. And about one third of this variation in residual feed intake or residual energy corrected milk yield was related to converting gross energy to metabolizable energy. And of this variation, it was about 85% could be attributed to digestibility and about 15% or a little less to methane. So methane was not any big player in determining differences in feed efficiency between the cows. And about 2/3 of these differences were related to improved efficiency of metabolizable energy utilization for maintenance and milk production. So this picture gives some numbers for a cow weighing 200 kilos, dry matter intake 20 kilos, and energy corrected milk yield 30 kilos. So about 30% of the energy is lost in feces. Milk production represents about 26% of variation, and heat production in this cow is the greatest energy loss. About 19% of the total energy intake can be related to heat production from maintenance, and about 15% from heat production from milk production. And methane is about 6%. So if we are going to improve feed efficiency, I think we should have the main focus in these greatest losses, feces and heat production. So this describes variants of different components related to feed efficiency, dry matter intake. When the cows have eaten same amount of dry matter, are same body weight, and have same energy balance. So milk yield is the greatest source of variation here, because it is an output side, and if we look the energy losses, the greatest variation is in heat production, and the next biggest is in feces. Whereas methane is here, it is quite small, it contributes quite small to differences in feed efficiency. Next, please. So this shows when we rank cows according to residual feed intake or residual energy corrected milk yield, about 1/3 to low, medium and high groups. If we look residual feed intake, of course by definition it decreased with improved feed efficiency from 18.5 to 15.9 kilo. So there is quite big variation in feed efficiency. And of course residual energy corrected milk yield, because it is milk yield at the same dry matter intake, body weight and energy balance, then of course there is no differences. If you could look energy corrected milk yield for residual feed intake groups, it is same because dry matter intake decreased. But it is, I would say, it is surprisingly big difference in energy corrected milk yield at same dry matter intake. It was about 6 kilo difference between low and high efficient cows. And these differences, if you look digestibility, there was about 2.5% unit difference between low and high efficiency cows, and heat production decreased with improved efficiency. In methane, the differences were small. Next, please. So if you look the methane intensity, methane production per unit of milk or energy corrected milk, so selecting cows for improved feed efficiency, it will clearly improve methane intensity. And more, the differences were greater if we expressed feed efficiency as residual energy corrected milk yield. Next. So potential for measuring feed efficiency in GreenFeed. In respiration chamber studies, carbon dioxide production was a good predictor of feed intake. So because it takes also into account, in addition to production and body weight, it takes into account differences in efficiency. Also, the coefficient of carbon dioxide is only about 1/3 in this Brouwer equation of the coefficient of oxygen. In calculating heat production, we can predict heat production relatively, I would say very well, even from carbon dioxide production, because oxygen and carbon dioxide are very strongly correlated. Variability in this respiratory quantity is very small when the cows are at about similar states of lactation and fed similar diets. So if carbon dioxide or production or oxygen consumption could be measured reliably by GreenFeed, it would be a powerful tool in ranking the cows according to feed efficiency without measuring feed intake. That's what we all know, that it is very difficult in practical farm conditions. Pekka. Yeah, then we try to use residual carbon dioxide as a measure of feed efficiency, and it was very strongly related to residual feed intake. So this is just a picture showing the close relationship between carbon dioxide production and heat production. So even if we don't know oxygen consumption, heat production can be predicted quite accurately. So adjusted residual standard error of mean was only 1.8 megajoules. That is about heat production per 1 kilogram of energy corrected milk, or even less. There were some statistically significant effects on these residuals, but quantitatively they were small. Probably if you want to make this prediction of heat production more accurate, you may take these factors into account in predicting heat production. Next, please. So these are the figures showing that residual carbon dioxide production was very strongly related to residual feed intake. And similarly, it was related to residual energy-corrected milk yield. Next. And if we could take into account differences in digestibility, the relationships would be still improved. This is because about 1/3 of this variation in residual feed intake or residual energy-corrected milk yield was related to differences in digestibility. So these are data from GreenFeed studies at SLU in Umeå, average repeatability values from 12 different experiments. As we can see that for total carbon dioxide and oxygen consumption, R square values are about 80%. So it looks that the between curve differences can be determined well with this system. For methane, repeatability is a little bit less, and it can be related to this greater background concentration, and also that methane is excreted in peaks, and whereas oxygen consumption and carbon dioxide production are more stable. We will put some other repeatability values from the same studies for comparison. Milk yield was higher, but dry matter intake and energy-corrected milk yield were at about the same level. I think we can understand better that how well or poorly these parameters are, or how repeatable they are. And it looks that carbon dioxide and oxygen, they are about at the same level of repeatability. We could think that milk fat concentration is rather repeatable measurement, but actually the repeatability value in these data was lower, probably because there is variation in milk fat content depending how empty the udder is, milk, and also sampling errors. Next, please. So then we have to go a little bit further in this. Then we made comparison between respiration chamber and GreenFeed that look at this in Jokioinen. This respiration chamber system is, this picture is from Danish system. What I heard that the Luke system is copy-paste system of this Danish system, and here is a figure of GreenFeed system. So we have just got some preliminary results of this comparison. Next. So we made this study using 32 Nordic red cows, switchback design, first GreenFeed period, then respiration chamber, and another GreenFeed period. GreenFeed periods were both 12 days, and respiration chamber period between these two GreenFeed periods was 3 days. We had about, in each GreenFeed period, the average number of visits was about 50. And the smallest were around 20 visits. We were feeding the cows grass silage-based diet as total mixed ration. Next. So this is the relationship between GreenFeed and respiration chamber. Carbon dioxide production, I think it is considering that the range in data, what Alex was talking here before, it was rather narrow, and that explains that why the correlated relationship is not. Oh, we can say that it is high, but probably good. And if you look this random variation, what it is, root mean square prediction error around this regression line, it was 6.6%, what I think it was pretty good prediction. And also intercept was close to 0 and close to 1 and intercept close to 0. Next please. For oxygen, the relationship was even a little bit better. Prediction error 5.6% and intercept close to 1 and slope close to 1 and intercept close to 0. That they were not significantly different from either 1 or 0. Next please. I think that even of these differences, some of these can be random differences, but part of it can be systematic differences. That when we look the relationship between difference in oxygen consumption and carbon dioxide production, they were very strongly correlated to each other. What I interpret that there can be differences in feed intake and production levels between GreenFeed and respiration chamber periods. So we will get later on this data that we can look, but my guess is that some of these residuals is related to differences in intake and production level. Next please. So these are from Abdullah Guina's PhD student. He made a feeding experiment starting immediately after calving, about 20-day feeding experiments, about 22 cows, and intake, production, digestibility and gas exchanges were measured at different stages of this production trial. And this is relationship between predicted energy balance, and it is just using tabulated feed values and requirements, and on y-axis is energy balance measured by the GreenFeed system. And there was quite good relationship there, and the slope 0.69, I think it makes sense because this x-axis is measured as metabolizable energy and y-axis energy retention is measured as net energy. So this regression coefficient means that energy efficiency for body energy gain was 69%, what is close to these different energy evaluation systems. Okay, next please. This is also data from Abdullah's study. This curve here, it shows changes in energy balance related to weeks of lactation, so it was really negative at the beginning of lactation, and at about 8 weeks of lactation, it was around 0. At the same time, there was changes in milk fatty acid composition. Early lactation, the proportion of long-chain fatty acids was clearly higher, and then it decreased with increasing energy balance, but when about 0 energy balance was reached, thereafter the changes were quite small. And of course at the same time the opposite trends were observed in de novo synthesized fatty acids, that they were low at early lactation when the cows were in negative energy balance. Next. And they were also looking at simple correlations. The novo-synthesized fatty acid, they were strongly related to energy balance, as could be expected, and especially these 18-1 fatty acids, they were negatively related to body energy balance. Part of these 18-1 fatty acids that are excreted in milk, they come from body tissue mobilization. Next please. So the efficiency of ME utilization, we have 5 different feeding experiments where we have calculated this KL value of ME utilization for milk production above maintenance, and milk energy is corrected for 0 energy balance. And we got the range from 0.660 to 0.668 for 19 different treatments. I think this corresponds quite well, for example, what is this default value in different energy evaluation systems like NRC. Digestibility was used in these studies, either acid insoluble as or INDF, that can increase random error. And in some studies, urinary energy was estimated by empirical equations. Next, please. So, some conclusions. We have had high repeatability of gas exchange values and close relationship between GreenFeed and respiration chamber preliminary gas data. And this relationship is likely to be improved when differences in intake and energy corrective milk yield are taken into account. And we have also got good relationship between ME balance calculated from estimated energy intake and requirement of when energy balance is measured by GreenFeed system. And we have also got expected correlation between milk fatty acid composition and energy balance estimated by or measured by the GreenFeed system, and biologically expected values for ME utilization for milk production. Okay. Residual carbon dioxide is a good proxy for residual feed intake and residual energy corrected milk yield in respiration chamber studies. And our results from this GreenFeed chamber comparison, I think they are quite promising that this system could be used also in practice for evaluating or ranking the cows according to feed efficiency. It is possible to use either residual carbon dioxide, residual oxygen or residual heat production as proxies of efficiency. I would say that these measurements, they should be made in sometimes in mid-lactation when energy balance is close to zero, probably having 2 to 4 week periods to get reliable data on gas exchanges. And milk fatty acids, this what we could get normal milk analysis with this mid-infrared spectra can be used as an indicator of negative energy balance, so that we don't interpret cow mobilizing body fat as an efficient cow. And of course, body condition scoring can also be used as an indicator of this. Because it is not possible to measure body weight change accurately from body weight change during short experimental periods. Okay, thank you.